What's going on, class? Welcome to lecture number 4. Hope you all are doing well this morning, afternoon, whenever you're watching this. We're going to go ahead and jump right in and pick up where we left off in our last video, our last lecture, and that was with Hooke's law. Now, to remind you, Hooke's law is the first law we're introducing that not only shows a relationship between stress and strain, right? But it also introduces a material property known as modulus of elasticity. So it's the relationship between stress and strain, something to keep in mind, and it goes like this: sigma equals E epsilon. Sigma here is going to be our normal stress. E is our modulus of elasticity, or in other words, elastic modulus. And then epsilon is our strain, normal strain. And E, again, is a material property, and it is determined experimentally. Now, for a second, we're going to take a pause here with document cam and come over here and look at our screen. Here we have a picture of reinforced concrete. For those who do not know, this is felt reinforced concrete here. And inside of this reinforced concrete are steel bars, and steel is put inside reinforced concrete to give it additional strength. Concrete is very strong in compression, but steel is strong in tension. It also has a little bit more give, as we're going to talk about, as it begins to fail. So take a look at this, right? This is a typical specimen whenever we are testing metal materials, aluminum, steel, things of that nature. And what we have here is on the ends, there are threaded ends here that typically go into our tensile testing machine. And we call this point in the middle, the point that we are examining, our gauge length. So L naught is measured between two designated points. In this case, it's 2 inches long, our gauge length that we're going to be measuring when we're doing tests like this with a specimen. And then we have an initial diameter of 0.5 inches using this right here. Now, what happens in the experimental labs and experimental circumstances is that we attach something known as a strain gauge. This is a traditional strain gauge. There are other ways to measure strain, right? But this is one of the most traditional, most used methods where there is a small electrical attachment sensor that is attached to the gauge length of our specimen. And then there is wires soldered to it and connected back to our computer device where we can measure the change in the length. But the change in the length is actually determined by looking at the change in electrical current, or electrical resistance rather, that flows through this pattern that is on this very, very thin sensor. So this here is a small little circuit. This is a zoomed in image or diagram of what that little sensor looks like. Electrical current goes through here. And as this thing begins to stretch, what happens? Well, this electrical current, the makeup, the shape of it also begins to change. And that then influences the resistance that a current experiences as it goes through that circuitry. And that resistance is correlated to the change in length, or the strain rather, that is happening right on that specimen. So as I showed you before, it is attached to the side of the specimen. That specimen is put into a tensile testing machine here in the middle of this device. If you ever went to a structures lab, materials lab, you would see this. And this upper head right here begins to move and apply tension to that specimen. As that specimen experiences tension, we're then, of course, tracking the change in the strain. And over here, typically these machines are very precisely controlled. They have a load dial where you can see how the load is doing. A lot of them are digital today. Not all of them are just strictly showing a little dial, but they have the load that's been applied so that you can correlate it between that and the strain you're seeing. And then there are controls. A lot of, like I said, hydraulic controls help to provide a precision to the change in the length or the applied load that this specimen is experiencing. From there, here's what I want you all to pay attention to. All right, from there, we are able to create a graph, right? A graph. This is what you call a conventional stress strain diagram. On here, you have two different lines, right, that kind of separate here. I want you all to pay attention to the one that is down at the bottom, because this represents what this particular specimen is experiencing while it is undergoing this mechanical test. And this is the experiment that gives us our material property, namely our elastic modulus. So as this specimen is first put into, if you all can see my little cursor there, first put into our testing device, both of the strain, which is the horizontal axis, and the stress, which is of course force over the area, is zero. As it load is slightly applied, the initial experience of this device is what we call elastic. It's the elastic region. So during this first linear region, if at any point the load is removed, it will go right back to zero because it's elastic. And so this first point going all the way up here to this first end of what we call the proportional limit, it is a perfectly elastic, perfectly linear relationship between the stress and the strain. And the modulus of elasticity, which we just talked about in Hooke's law, that big E, is just the slope of that elastic region. It's the slope of that elastic region. Or in other words, it's the rise over the run, the stress over the strain. So take a look back at this. It makes a lot of sense when you rearrange your equation, right? So if we were to rearrange this and solve for E, E would simply be equal to sigma over epsilon. Or in other words, the stress over the strain. Now, it's not a single value. We're going to do a little bit of determining that in just a second. But to continue on with this diagram so that you all can make sure you know what you're looking at here, there comes a point where it is no longer elastic. It's no longer elastic, but it began to experience more strain with less load or less stress applied to it. And so this perfectly linear line begins to tilt a little bit. And that's what we call our elastic limit. And shortly after it reaches this elastic limit, it begins to experience yield stress. And so now we move from elastic behavior, look here at the bottom, elastic behavior, to plastic behavior. As you go into plastic behavior, if at any point the load is removed, it would not necessarily go back to zero. Why? Because it's already begun to stretch a little bit. And this is where you begin to see the change in the diameter, of our specimen begin to take place. And I'll show you in just a second. A change in diameter begin to take place. And now we experience yielding after the yield stress has been surpassed. And after you go through a period of yielding where now there isn't really much stress being applied, but yet it is getting longer under that exact same level of stress, we go into this phase known as strain hardening. It's almost as if the material all of a sudden says, hold up, you're not about to punk me. I'm going to give one last effort. I'm going to give one last restructuring. And on a microscopic level, what's happening is they're shifting, right? They're shifting in the molecular structure of it. And so it actually begins to provide a little bit more strength than it was providing prior to. And now we experience this phenomenon known as strain hardening. So now additional stress has to be applied in order to continue to get an increase in strain. That's called the strain hardening. And then you reach a point where it can't go any further. There isn't any more strength or any more resistance to the stress that can be experienced by this device. And then this peak point, as you can see, is called the ultimate stress, or sigma sub u, the ultimate stress. From there, you don't need as much stress to be applied. In fact, it actually decreases as it goes down to what we call the fracture stress. Now, this last phase after strain hardening is something we call necking, right? That's how we know that it has already exceeded its ultimate stress, is when you visually begin to see the diameter of our specimen begin to get smaller, and that is what we call necking. What I think I'm going to do right here is I'm going to show you a video, just a little clip of a video that I found on YouTube that just kind of gives you a visual representation of what's happening here in this stress strain diagram. I'm not going to play the whole video, but I'll play enough so you can kind of see what I'm talking about. So here is another example of your dog bone specimen. That's another thing that we call it dog bone because they're larger at the ends and smaller diameter. Here, this green thing, this green gauge length right here represents the gauge length as I showed you, as I told you on our diagram before. And I'm about to play right here, right after it reaches its ultimate tensile strength, and you begin to experience or see, identify necking taking place in the specimen. So right there, as I hit play, there is a gradual decrease in the stresses applied because it's already reached its maximum. And as you can see, it's getting a little bit smaller before it breaks. And ultimately, a fracture is going to happen right there where you see the necking occurring. That, my friends, is necking right there. And as it is stretching, it is not increasing the load, but the gauge length is getting longer until ultimately there is a failure. There is a failure. So that is, as we said, our fracture, our breaking strength is how they're calling it here, our fracture strength. And this is an example of our engineering stress strain curve, our engineering stress strain curve. Now, let me tell you this really quick, moving forward, before we get off the screen. This is called the engineering stress and strain curve because to calculate this, we are using a value as if the diameter or the cross-sectional area is staying the same. However, in reality, just so you should know, this one up here, this lined up top, called the true fracture stress and strain. The true. This is taking into account that as you continue to apply this stress, there is a decreasing of the diameter. So what does that mean? That means that the value that's going underneath the force term load, let me come over here and show it to you. The value underneath the force, recall that, again, stress that's at the top of this equation is force over area, right? And just to be clear, and just to go back really quick, the engineering stress always keeps the initial cross section. It's not changing it as time goes on. Therefore, as this increase, this being constant, this is going to be directly proportional. However, when it comes to true, so I'll say engineering, but when it comes to true, the value is still F over A, but it also takes into account that this A is going to be changing. It does take into account that this A is going to be changing. So as that cross-sectional area gets smaller, true seeks to continue to divide it by its accurate cross-sectional area at that point. And many times, since the necking is going to occur, looking over here back here at our screen share again, because necking is occurring, that means that this is getting smaller. The area is getting much smaller. And so therefore, the stress could actually continue to increase even after it has exceeded what we call its ultimate stress. I hope that makes sense. That y'all got that? Y'all got that? So take some time to really explain that. There are a lot of videos online. You can go and look at some actual tests to see how this is determined. But the main thing now moving forward from this point on is that we want to make sure we know how to calculate and identify E. And what that simply means is when we look at our stress strain curve, strain of horizontal stress, and we begin to see this initial region, this elastic region here, before it begins to plateau and it strain hardens, then it hits its maximum and then it fails. When it comes to finding your modulus of elasticity, all you have to do is make sure you appropriately identify your elastic region, take the strain or the slope, take the slope of the elastic region, and that gives you your modulus of elasticity. That's what we want to make sure that you know how to do, right? So we'll come back to the plastic region over here. Beyond this point, right now, we're going to focus on the elastic region. right? You need to know how to understand this entire graph. You need to make sure you know what a stress strain curve is and you know how to draw it. But again, just for the modulus of elasticity, that's going to come directly from your elastic region. All right, let me do one more thing. I'm going to draw E, or not draw E, but write E this way, right? Because here's the way that obviously it is written in terms of Hooke's law. Sigma equals E epsilon, or E equals sigma over epsilon. But to calculate E using the graph, you're basically going to look at the change in the stress over the change in the strain to get the rise of a run, right? The rise of a run. Or another way, if you want to look at this in terms of, I think geometry is the class that we learned this in, but that's when we would look at, you know, y L minus y naught, or x1 minus x naught. All right, you can look at it that way. But here's what we're going to take to the bank, and here's what we're going to do right now in our first example, which is example 3-2. 3-2. Take a look at your textbook. Take a look at your textbook. And I want you to look at example 3-2. Very, very simple problem. Or to come out here and show you the whole screen. It gives us this chart right here. And it's basically some data. You can look at this as data that was collected from your tensile tester. You're in the lab, you ran a test, you had the donut bone specimen, and you got the stress and you got the strain of this particular material. And here's what the problem statement says. It says data taken from the stress strain test for a ceramic, that's the material, a ceramic, are given in the table. The curve is linear between the origin and the first point. So the origin is 0, and the first point here will be 33.2. They said it's linear between here and here. Plot the diagram and determine the modulus of elasticity. It also says the modulus of resilience, but we're going to focus primarily on the modulus of elasticity here, the modulus of elasticity. So what we're going to do right now is literally go back to, I think, geometry is where we did a lot of this, and even calculus, where we're going to literally plot. We're going to plot these numbers. So we'll start off by drawing a XY axis. This is important for us to be able to do and visualize. So start off with our XY axis. This is Y. This here is stress. Now, stress is going to usually be in some sort of units. And in this case, we got KSI. So kips per square inch. And then epsilon here, this is our strain. Technically dimensionless, but we'll write it as inches per inch. Right? This is our origin. 0, 0 in both cases. And we'll go ahead and start writing our increments here. Boom, 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 boom. Equally spaced. If it's not equally spaced, it's not going to look right. So 0.0, we'll call this 0.0005. This is 0.001, 0.0015, 0.002, 0.0025, and so on, 0.003. And we'll do some equal increments here. Now, for your homework, this will obviously be done online if you're using the Master in Engineering. And you're going to have to make sure you know how to use those tools to draw something like this. But here's, of course, we're going to be doing this by hand at this point in time, 50, 60, 70. All right, so first one, start at the origin, 0, 0. That's where we start. The next one says at 33, 33.2. So it's up here a little bit, and 0.006. So here, and the problem statement says that between that, our initial our origin, we have a linear. So I'm going to get this straight edge here, so I can draw a nice linear line there. No judgment on the hiccup there, but that's our linear line, right? And so we know that the slope of this is our modulus of elasticity. To continue the plot, the next line we got is 45. Oh, we got one of my lights flickering. All right, it's going to be 45.5 at 1. So here, doom 45.5 is somewhere in the middle. So that's going to come over here. We're just spotting. The next one, 49, coming up here a little bit, is going to be at 04. Boom. Come over here. So it's just right now beginning to experience plastic deformation, which is understandable because we know that that's how these things behave. Over here, wait, it's gonna be at 51. So we're just plotting, and this thing is starting to look exactly like we expect it to look. And then the last thing we have on our chart is 53 when it comes over to 0.222. Boom. All right, so we'll just stop there. Because ultimately we just want to know our modulus of elasticity. Now this is pretty simple though. We're going to, as I just wrote previously, find the change in the stress and the change in the strain. Well, what can we use as our initial and our final? If we're talking on the y-axis, knowing that is linear here, we use these first 2 points. So 33.2, whereas it started at 0. And then down here, we can use 0.0006 minus 0. And then we just do the math. This is straightforward. This is elementary math based on where you all are now in terms of what you understand. So let's see, 33 divided by 0.0006. And the answer, my friends, should be 333 KSI. Now you may have noticed something that you've noticed now that the units of the modulus of elasticity matches the units that we, matches the units that we have for stress. So E, what should be whatever unit stress is. Why? Because stress is in KSI. And then our strain is technically dimensionless. So KSI, this is our value for our modulus of elasticity for this particular problem. All right. Now we're going to go and continue on and go and do another example. This is 3-2. Right now, going back to our screen, I'm going to do another example that allows us to make sure we understand how this whole chart works, how these material properties work. And we are going to look in this case at problem 3-10. So just pull up the image here. Here's what 3-10 looks like. If you were to open your book, consult your e-text or your physical copy, you could see what the problem statement says, and I'm going to read it right now in your hearing. It says the stress strain diagram for an aluminum alloy specimen, right? Aluminum alloy specimen having an original diameter of 0.5 inches and a gauge length of 2 inches is given in the figure. Determine approximately the modulus of elasticity for the material, which is what we just did, the load on the specimen that causes yielding, that's what we're going to do, and the ultimate load the specimen will support. Now, what they've done is two things. They've tried to save space a little bit. So they've shown two parts of the exact same graph on the same image. This may come up another problem. So I'm glad you all are sharing this now so you can know how to read this. But what we have here is the first part, linear region, then it enters, it begins to yield in the plastic region. And I want you to imagine that this point right here connects to that point here, right? So if you were to take that in your mind and attach it to the end of this, that's really how the graph would look. But again, they want to save on space. And so for this top graph here, use these bottom numbers, these bottom blue numbers when you get into that part of the graph. And for this part of the graph, the initial part of the graph, you're going to use the black numbers here. So that's what we're going to do here as we prepare to solve 3-10. 3-10. So coming over to your paper, let's start looking at a couple of things right out the gate. What we need to be able to identify right out the gate is our yield strength, right? So our yield strength, we can see right here, we can approximate by looking at our image that it begins to yield right here around 50 KSI, 50 KSI. So the first thing I want you to write is your yield strength, sigma sub y, being 50 KSI. All right, I need you all to write that. That's helpful because now we can establish when we are no longer in the elastic region. So every stress value beyond 50 KSI is not elastic, right? So that's not going to be our elastic modulus. Now, what we can start off by doing is also recognizing that we do not know the cross-sectional area. All we have here in our image, what we were told before, is that we have a diameter of 0.5 inches squared, right? 0.5 inches squared. Because it's going to access the ultimate load or ultimate force, what we need to be able to do is to know that this right here, 50 KSI, is equal to some force over an area. Now, we don't know the force because that's what we're going to try to find the load, but we need to find the area. How do we find the area? Well, we take this diameter that was given to us and we calculate it. So the diameter is 0.5 inches, and the equation for that is pi d squared over 4. Pi d squared over 4. Let's go ahead and plug in our 0.5 inches over 4 squared. And we can get our area. Pi d squared. And you should have, if your calculator agrees with mine, 0.1963 inches squared. That is the area, cross-sectional area. Now, for a second, let's make sure we can start calculating some things. We should have what we need to start moving forward. Determine the modulus of elasticity. Well, the first thing we can do is get the modulus of elasticity. Now we have our area. That's not needed for the modulus of elasticity. We can actually just take this and find the modulus of elasticity by calculating the change in stress, 50 minus 0, over the change in strain. What is the strain that is being experienced right at 50 KSI? And I'm sorry, let me tell you something. I actually told you something the opposite earlier. So these light blue lines here is actually the number, light blue numbers, it's actually the numbers that is going with our bottom portion, not our top. So the top portion has larger strain values because, again, we're imagining it's on this side. So the light blue is going for this. So what we see right here is at 50 KSI, it is experiencing a strain of 0.005. So right here on our calculation of the modulus of elasticity, we would do 0.005 minus 0. And from there, we can calculate our E. 50 divided by 0.005, basically. And that gives us a modulus of elasticity of 10,000 KSI. That's the first answer. Modulus of elasticity is 10,000 KSI. Now we're going to come back to area because we already calculated. We got ahead of the game. The next thing that we need to do is the load on the specimen that causes yielding. Well, we know that yield stress is 50 KSI. Coming back over here, we're going to set 50 KSI equal to F over A, right? And we want to know the load, meaning the force, not the stress, but the force. So now let's go ahead and plug this in here. 50 KSI again is equal to F, which is what we're solving for, over 0.1963 square inches. Let's do algebra, because in order to solve for F, all we do is multiply that by both sides. So F in this case should be 963 times 15. 9.82. 9.82. What is the unit? What is the unit? Well, you can know that this unit here, area is square inches. And then this one is kips per square inches, KSI. These cancel out, leaving us with 9.82 kips. Which is the second answer that we need for this problem, right? So we got the modulus of elasticity, boom. We got the load on the specimen that causes yielding by taking our yielding stress and setting it equal to what we know is the equation for stress. And then lastly, it says, what is the ultimate load? The ultimate load that this thing will experience. Now, load, keep that term in mind, because some people trip up. When they say load, they continue to start putting in stress. They look at the graph and say, oh, that's it. Here's the ultimate load. But we don't want to do that. We want to get the ultimate stress and then back calculate based on the area, the ultimate load. So looking at this again, we can identify first and foremost the ultimate stress. What is the ultimate stress, right? What is the highest stress value that we see? Well, this is the second part of the graph coming up here. And I would say that the peak is right about here, which in terms of stress corresponds to, let's say, 68 KSI. KSI is our ultimate stress. So we're going to do the exact same thing we did when we found the yielding load. We're going to find the ultimate load by dividing it or by multiplying it by area. So one way that people look at denoting ultimate load is by using P sub U. Again, P, F. There are other ways that we can, there are both ways we can just represent force, right? So this is Fy, right? As a matter of fact, I'll just call this P just for consistency. This is Py. That's the force we have here. Again, F could be P, doing that for consistency, y'all. And then now here is Pu, the ultimate. So that is going to be doing the same thing, right? The area, 0.1963 times the stress. We've determined that to be 68. Let's see if your calculators concur with mine. 0.963 times 68. And what I have is 13.35. 13.35 kips. And that, my friends, is our ultimate load. Makes sense? Makes sense? I'm sensing, I'm believing that your head is nodding. You know, I can't see you. All right. So that's what we are now in terms of our second example problem. All right. So what I'm going to do right now, I'm going to introduce you to a few more concepts moving forward in chapter 3. And I believe this concept right here pops up that I'm about to talk about in section 3-3.3, and that is ductile materials. All right, you need to know what a ductile material is, or when the material is ductile, what we're referring to. What we're saying is that this material allows for more change in size before failure. Think of ductile materials as a material that's able to change quite a bit and yield and neck and change this cross-sectional area a little bit more before it fails. And that is the opposite of what we consider brittle materials. Brittle materials, on the other hand, they allow very little change in size before failure. So an example of a ductile material would be like rubber, right? Rubber begins to change its size quite a bit as it's being stretched before it actually breaks. But then an example of a brittle material would be like a ceramic. A ceramic doesn't stretch like rubber does. It pretty much just breaks without you even recognizing it, at least not visually. When it comes to how it changes, right, we're going to look at the percent elongation. These are some equations you can take with you. Percent elongation, right? And that is the length, the final length minus the initial length over the initial length, convert it to a percentage. And then I want you to look at the percent reduction in area, right? We're talking primarily cross-sectional area, percent reduction in area. And so that's going to be sort of the flip of the equation. You got the initial area, pay attention to this, minus the final area over the initial area. All right, so take note of these two equations as it relates to our concepts that we're talking about right now. Another thing I want to show you is when we're talking about, coming back over here to our screen share for a second, when we're talking about the plotting of graphs like this, right? When you're going to actually plot it yourself, and sometimes you can get to a point where you're like, all right, where do I actually identify as its yield point, right? Where do I really identify? I can eyeball it sometimes when the graph is nice and clean, but what am I going to do? Well, there's this notion known as the 2% offset method, and I have this already drawn here, right? 2% offset method, or 0.2% offset method. Coming back to the document count, I've drawn this little equation, this little stress strain diagram here, right? So when it comes to using the 2% offset method, it's a consistent way to make sure everyone is working at the same point, right? Everyone's working at the same point. And so what it does is it takes 0.2%, or in other words, 0.002, and it shifts that from the origin here. And then we draw a line from that point that is parallel, right? These two lines are ideally parallel from that point on the strain axis up to the curve. And we're going to use that line sort of as our consistent reference from which we determine our modulus of elasticity. This is just, again, a method, a consistent method to make sure that everyone is using the exact same slope whenever we are trying to determine the modulus of elasticity. So keep that in mind when it comes to the 2% offset method. That shows up again. You're going to shift over 0.2%, and you're going to draw a line parallel with your elastic region and connect it to the curve. And that is what you can use to determine your modulus of elasticity with that method. All right. A few more concepts, a few more equations. Now you may notice, again, going back to Hooke's law. Hooke's law, just to draw it right out again for ease of reference. Sigma equals E epsilon. Shows your relationship between the stress and the strain of a material. Now, remember I told you though that there's necking, there's time when the cross-section or area is changing as stress is being applied. So we're going to look at something that relates the change in the strain laterally with the change in the strain longitudinally. And this particular thing is known as Poisson's ratio. Poisson's ratio. All right. And this is represented by the Greek letter mu. And what it does is it puts the latitudinal strain over the longitudinal strain. Right? So strain along the axis, it's on the bottom, that's longitudinal. And the latitudinal strain is actually going in the opposite direction, because as it's getting longer, the cross section or the diameter is getting smaller. So in order to keep this number positive, it puts a negative on the outside of it. Sorry about that. Keep Poisson's ratio in mind. And then last thing I want to show you really quick. I'm sorry, not last thing. I got two more equations to show you before we do one more example. All right, I want to show you here that there is this relationship, just like Hooke's law, but deals with stress or shear, does with shear. So you have tau, which is shear stress, equals G times gamma. This here is shear strain. So this is the Hooke's law in terms of shear. And so what we call this, instead of calling the modulus of elasticity, we call this the shear modulus. The shear modulus. So that's another equation to keep in mind. Your shear modulus. This is for normal. This is for shear. This is Poisson's ratio, which shows the relationship between the latitudinal and the longitudinal strain. And then one more relationship, this last equation I'm going to show you. It connects, or it helps you to know the relationship between the shear modulus and the modulus of elasticity, E. And this equation looks like this. G, the shear modulus, is equal to the elastic modulus over 2 times 1 plus mu. What is mu? Mu is Poisson's ratio. So Poisson's ratio is the key that unlocks the relationship between your shear modulus and your normal elastic modulus. Make sense? Cool. All right, so we're going to do one more example that's going to tie all this together. And that particular example, I'm going to put the image on the screen right now. It is image right here. And it has the problem statement 3-27. In case you're all ever curious, there's 3, there's 27. So just to write it on the screen, 3-27. That's the problem we're doing, 3-27. And here's what the problem statement says. It says the elastic portion of the stress strain diagram for an aluminum alloy. Now, just keep in mind to tell you the material, there will be some problems that have multiple materials later in the course. You want to make sure you can differentiate what material is which. But aluminum alloy is pretty much all we're dealing with in this case. So that's just irrelevant information to our calculations in this case. The specimen from which it is obtained had an original diameter of 12.7. I'm gonna go ahead and write these things out. So 12.7 millimeters. And it had a gauge length, original gauge length of 50.8 millimeters. When the applied load on the specimen is 50 kilonewtons, so they gave us an applied load of 50 kilonewtons. This is a force. This is not a stress. So 50 kilonewtons. The diameter then becomes, so at 50 kilonewtons, the diameter then becomes 12.67494 millimeters. That's the diameter at this stress. So it's slightly less than the initial diameter. Determine Poisson's ratio for the material. So let me walk you through this really quick. First thing we need to do, what can we do right off the bat? We can look at this and see that we can determine our modulus of elasticity because we see exactly where the yield stress is. And we'll do that by putting 490, right? That's MPa at 490 over 0.007 minus 0. If you were to do the math on that, because this is MPa, you're going to get 70,000 MPa. Or you can just say 70 GPa, gigapascals. After that, we want to look at we want to find Poisson's ratio because from there, that's going to answer our problem. So Poisson's ratio is a negative strain latitudinal over strain longitudinal. That's what we want to find. This is basically our endpoint. So we can take our module of elasticity and we can begin to start calculating our stress and our strain, because in this case, this is strain longitudinal, and achieve that. So stress is equal to force over A. We got 50 kilonewtons. And we know that at that point, there is a diameter here of 12.67494. So let's go ahead and let's put the equation pi d 12.67494 squared over 4. Let's go ahead and put that right into the equation. We could do the math straight up in that. What I have here, if you concur, is 394.7. So it's 394.7 MPa. That's our stress. And then from there, we can get our strain, because we have our modulus and then we have our stress. So our longitudinal strain is now equal to stress over E. So we got 394.7 MPa over 70,000 MPa. So our longitudinal strain is, you should have 0.00568 millimeters per millimeter, just to keep things moving. So now we have this bottom part of our Poisson's ratio, right? The bottom part of our Poisson's ratio. Then from there, we need to determine the latitudinal strain. The latitudinal strain. And the latitudinal strain is a change it can be calculated by looking at a change in the diameter that we've already determined is taking place. So the change in diameter would be the initial diameter, 12.7, minus the final 12.67494 over the initial 12.7. We do the math there. And I'm sorry, I made a mistake that I didn't want you all to make. These are supposed to be switched. These are supposed to be switched. Boom. Because remember, it's going to be the opposite direction. It's going to be the opposite direction. So let me just rewrite that again. Let's go 12.67494 minus the initial over the initial. Let's do the math on that. 12.67494 minus 12.7. And that answer should be a negative 0.00199732. Right? That's your latitudinal strain. And again, it's written that way and it has a negative because in our Poisson's ratio equation, we have an additional negative on the outside, which is what's going to allow this number to be positive at the end. So let me go ahead and write that here. So you have a negative times a negative 0.0019732 over E long, which we found this here to be 0.005638. And now we can calculate this here to get the answer. This is a ratio, so it shouldn't have any dimensions because both of these dimensions, or both of these numbers are dimensionless, or millimeters over millimeters. And if you were to do this correctly, this number, if your calculator agrees with mine, should be 0.35. That, according to the problem, is our Poisson's ratio and what we were solving for. So we had to do a number of things. Obviously, we had to start things off by identifying what was our initial diameter, our initial gauge length. Now, our gauge length was not utilized the way we thought it would be used, but we did see what happened to the diameter when it gets to 50 kilonewtons. We can use the 50 kilonewtons in the chart that we're giving just to simply get our elastic modulus, or modulus of elasticity. We know the relationship between the modulus of elasticity and stress and strain to then back calculate based on the area, the force, our stress, and then ultimately our longitudinal strain. From getting our longitudinal strain, we have one part of our Poisson's ratio, the bottom. Then we need our latitudinal strain by subtracting this final diameter length or subtracting from it the initial diameter, getting that negative number there. We can then place it in our Poisson's ratio equation. Remember, the negatives cancel out, and now we have a value of 0.35. I hope that makes sense for you all. I hope you all are good to go from here, because that will conclude our lecture for today. And make sure you understand the diagram, Hooke's law, Poisson's ratio, and how all this applies to the material property of whatever we're testing or whatever you're using. All right, I'll catch y'all on the flip side. Peace.